Okay, welcome everyone. Welcome to the first class of ECE 346, Digital Signal Processing in the spring semester. My name is Wahid Bajwa, and I'll be your instructor throughout this class. This is the handout of the class. It's posted online. I'm not printing it because I found it over the years to be just a waste of paper. So if you're interested, you can just go to Sakai page or the course website and find details. We'll be going over some of the details in a little more carefully. So my address, if you ever want to come to my office, I do encourage you to do that. It's 723 Core Building. The way you can communicate with me is email, which is wahid.bajwa@rutgers.edu. I will be using the Twitter account for communicating with the class. If you want to talk about something, the hashtag is RUECE346. All of these lectures, to the best of my abilities, again, I'm not promising, but I'll try my best, will be posted on YouTube. The channel name is SIG Processing. The course website, I hope you guys know where to find that. Sakai page, you should all be uh, signed up by now. If any one of you has not been getting my Sakai emails, please talk to me because by this time I have already sent like 4 or 5 emails at least. I will be maintaining office hours, which will be immediately after the Monday class for an hour. And if you want to meet me other than those times, you're more than welcome. There is a Doodle page which you can use to request meeting times with me. And it's available on my website. It's listed as doodle.com/Bajwa. You can go there. We have 2 teaching assistants which will be alternating between the class and the lab. You will see them in the lab too. Just as a clarification, I am not in charge of the lab. If you have any lab related questions, please talk to Professor Orphanides or the TAs. Okay. The TAs names, they have been decided. We'll announce them soon, and we'll also decide what are their office hours that they will be maintaining. Okay, so the required text for the course, this is different from last year. It's based upon the feedback that I've received in the last 2 years of that I've taught this class. I'm now changing it to a text by Sanjit Mitra. We'll be using the 4th edition. Its name is Digital Signal Processing, a computer-based approach. You are more than welcome to purchase international editions or what have you. Just be careful about the fact that some of the practice problems that I may give will be simply, well, here is the problem number that you should be solving. Okay, and the problem number may not be the same for international student. I don't know. It may or may not be. You should be careful about that. Prerequisites, I'm sure if anyone of you did not clear ECE 345, you wouldn't be sitting here, but just want to make sure. Prerequisite is the linear systems class. You should have a good understanding of some of the basic material, although we will be doing a very brief but quick review of those concepts. Okay, and you should be comfortable with programming in the MATLAB. Okay, so some of the more important details, the breakdown of the course. There's a 2% of the prerequisite quiz, which we'll be having in about 2 weeks' time. I'll formally announce the time. Prerequisite is just going to test you on the knowledge that you gained in ECE 345. As I said, even though I'll be putting these lectures on YouTube, that's not a license to not attend the class. And to ensure that, I'll be having some random attendance taken in the class. And the way that random attendance will work is the following. Everyone will start 3%, everyone gets full marks. And then on random days, I'll draw some names in a random fashion. And if that person is present in the class, that's fine. They stay at 3%. If they are not, then they lose half a point. Not half a percent, but half a point kind of thing. Okay? So it's, again, it's not licensed not to come. And on top of that, you know, some of the attendance might be taken late, but it's not, you can't say like, I came 5 minutes before the class ended, so I should be counted as present. Okay, that's not how it will work. So be wary of that. The other thing we'll be doing is Sakai quizzes. So if you miss a class or you have forgotten what we learned in the class, we'll try to reinforce that through quizzes which will be offered through Sakai. And the idea is that you keep up with the material, because this is a class where you cannot wait till the exam and then say, well, I'll just cram it in. Okay, this is a mathematically intensive class and you have to stay on top of the material. So what we'll be doing is, on a weekly basis, making sure that we understand what we have learned so far through giving these small quizzes. So that will be 5% of the course. We'll have graded homeworks, which will be 5%. There will be some practice problems, which will not be have any percentage. There will be a final term project, which will be team-based. It will be 10%. I'll follow the same principle that I followed last year, which is about finalize the details about a month before the semester is about to end, and you'll form teams of 3 to 5 people and then submit it at the end of the semester. There will be 2 in-class exams, 40%, and a final exam, 35%. Yeah. In terms of general policy, you can keep track of this document. Basically, I already explained the random attendance policy, and the next policy is that of late homework submission. And the idea is that every one of you will get some emergency where you can't submit the homework, so you don't have to come to me and say, oh, can I submit it late? Every one of you gets 1 late submission free of, so you essentially have a pass of 1 late submission. You get to decide when you want to use that, okay? If you use it in your first homework, that's it, it's gone. You also get to have a second free pass, but that free pass comes with a 30% penalty, okay? And after that, it's end of story. So after that, if it's emergency or whatever, it's not going to work. So these are really passes for emergencies, right? And you should use them if you really think you can't work. Don't spend them in your first 2 homeworks and then say, oh, now I have a real emergency, what do I do? Okay, so I've created this policy so that you don't have to come to me and ask, well, I got this and this, can I submit the homework late? Yeah. Quiz makeup policy. The quizzes will be online. There will be a time when you have to take it. If the deadline is, typically what will happen is the quiz will close on Sakai before the next class starts. And if you don't take it by that time, there won't be any makeup, okay? Because there will be enough time for you to have done the quiz at your own time. If you don't do it, no makeup for that. Exam policy, again, this is a change from last year. I'm going from open book and open notes to closed book and closed notes. The reason is not that I somehow want to torture you by doing it closed book. What I've seen in the last 2 years is that when I give open book and open notes, students presume that somehow they can come on the exam day and just look through all the book and somehow be able to solve the problem because it's open book. And it never works for them. So it gives them this false sense of security that somehow not study, open book means not needing to study. So I've now changed that. What you will get is you are allowed to bring 2 two-sided letter-sized pages for midterm exams and 4 two-sided letter-sized pages for final exam. That's it. You print anything you want on those pages. Other than that, it will be closed books. If you want to make up exam, you have to give me at least a 7 days notice. You can't email me a day before the exam and say, looks like I won't be able to make it to the exam. Well, you are more than welcome not to make it, but then you won't get a makeup. Okay? Grading policy, I do curve the grades. But again, that's not a license for all of you to collude. You say like, okay, since average is going to get a B, how about all of us do crappily on the exams and all of us will get Bs, right? So to prevent that, in general, if the class was behaving as I expected to behave, people who are on average, above average, close to average, will get B, then B plus, then A, and similarly down below the average will get C plus, C, D, and hopefully no one will get an F. Okay? But if the whole class performs worse than what I was expecting, then average could easily get a C plus too. So it will be curved, but it's not going to be just blind curving. Okay? And that just covers all the course related administrative stuff that I had to talk about. I do want to say that I've put down a few bullet points here for you to help you make learning this course easier. All of you have taken 345, and if you thought that was difficult, well, DSP is a follow-up to that, so it will be even more difficult. But it can be made easy. And how it can be made easy? By you and I working together. So I'll try to do my best to convey the information. I'll try to do my best to help you if you come to me. But you have to do your best by making sure you stay on top of what is assigned. Make sure you follow up all the reading assignments. I'll be giving regular reading assignments. They will all be posted on Sakai Lessons, the lessons page. I'll be assigning some maybe supplementary videos. I already did that for this class. I saw that only half of the class watched those videos. Now, I understand some of you guys might be already familiar with those concepts. That's okay. But if you don't think that you can somehow not work hard and do fine in the course. Okay, so it's a partnership. I'll help you do better, but you have to help yourself too. Okay, I am always there to help you if you come to me. I can't keep on emailing you personally and say, oh, do you guys need help? Okay. The TAs are a great resource. Use them. And that's all that there is to say about administrative stuff. In terms of the course outline, in the first week or maybe week and a half, what we'll do is talk about some introduction to signal processing, and we'll talk about some review of 345 concepts for signals and systems. Then the next few weeks, what we'll talk about is sampling of continuous time signals, aliasing, sampling theorem, discrete time Fourier transform, and details like that. And at the end of that, we'll probably have our first midterm. Then after that, the next big chunk of the course will be about discrete Fourier transform and its use in terms of analysis, in terms of LTI systems. And after that, we'll have probably our second midterm. And then the last 2 or 3 weeks will involve filter design and so forth. And after that, we'll have our final. So this lecture will talk about the very basic question, which is, what is signal processing? I think it's an essential question in terms of whichever course you are taking, the first thing that you should ask yourself is, why am I studying this course? So we are sort of trying to answer that question. What is signal processing? And if you want to understand what is signal processing, then the first question we have to then ask in turn is, what is a signal? So to answer that, we'll ask the question, what is a signal? And so a signal is anything. I'll call it a thing because it can come in different shapes and forms in terms of physically, but anything that conveys information, and information is a subjective term too, so I'm putting that in quotes also. Anything that conveys information is a signal. Okay. We'll make this abstract definition a little more practical by talking about examples. But in general, when we talk about signals, and in the modern world, many people, when they say signal, sometimes they also call it data, right? Which is just a way of saying that is a digital signal. A digital signal is often called data. But if we talk about broadly, where do signals come from? We have basically two separate classes that we can talk about. One is that the signal can be natural, or it can coming from a physical phenomenon. So it is not man-made, it's natural. And the opposite side of it is that the signal can be man-made or synthetic. So let's look at examples of the two. What could be some examples of natural physical phenomena? If we talk about natural, then we have voice or speech. We have climate parameters, temperature, pressure, carbon dioxide emissions, all those readings, sunlight intensity. Right? So climate parameters. Any visual scene is a signal. I'm looking at this 2D thing, and if someone of you were to raise your hand, that visually is conveying some information to me. Right? So the visual scene, 2D image, or if I'm looking at in a 3D, so visual scenes are signals. You can have seismic activity in a region. You can measure that, vibration in the earth, that's a physical signal. In terms of man-made or synthetic, let's talk about example in that case. If I count the number of likes on a Facebook page, so counts of likes on a Facebook page, that's a signal. It's not signal in the traditional sense that you think of. It's completely man-made. It's just counting 1, 2, 3, 4, 5, 6, right? For different pages, you have different count. That's a signal. Okay. You could have, on Google, you search different words. When are different words searched and with what frequency? Let's say you search for signal processing. What times of the day they were searched and what frequency they were searched at. That's a signal too. So frequency / time of searches on on Google. Let's say I am sending tweets about the class with this hashtag RUEC 346. The times at which these tweets go out, if I record those times, that's a signal. Okay? So timing information of tweets is a signal. So we have addressed what is a signal. We were trying to ask what is signal processing. And the answer should follow simply from the definition of signal. So we defined a signal as something that has information, anything that has information. And what is signal processing? Signal processing is the ways, the means of extracting information out of signals. So anything that you do on data or on signal to extract any information, you will call that signal processing. So signal processing is really about extraction of useful information from signals and there could be another view of it, which is that you sometimes don't necessarily extract information right away. You want to do some sort of manipulation of the signal to achieve some desired effects. So manipulation of signals to produce desired outcomes. Okay. Now let's take a look at the first the example of if you are given a signal, what information you want to extract is very much application dependent. Okay, you can't extract the information out of someone's grades. You can't extract the same type of information as you can extract from, let's say, stock market data, right? There are different kinds of signals, and the kind of information that you want to extract out of those signals will be completely different. It's application dependent. So if you are into studying earthquakes, for example, then one kind of a signal will be seismic activity. You have seen all those movies where, you know, an earthquake is coming and they start moving those needles, and right, they are measuring earth vibrations. That's seismic activity. Okay, so that's a signal. Now, if that's a signal, signal processing can be used to extract what kind of information out of seismic data. It depends upon what application you are doing, but for example, one of the types of information you could extract is a tsunami, for example, coming to a region? Right? Is there a strong enough earthquake, and is there a danger of tsunami coming to a region? So is a tsunami coming? That's a very key piece of information. If you can extract it in a timely manner, you can end up saving hundreds of thousands of lives. Okay? But it completely depends upon the type of application you are working with. Now, on the other hand, if you talk about manipulation of signal, let's say you have some music, which is a signal, and you want to manipulate it using signal processing. What you want to do is perhaps increase the bass of that music. So you have an equalizer, you want to increase the treble, or you want to adjust how the tune sounds. Right? That's an example of manipulation of the signal. You're not necessarily trying to extract any information out of songs. Some songs may have some information, I don't know. But you are trying to manipulate it to achieve desired outcomes. Okay? So you want to generate from the music, you want to generate something that has higher bass or treble. Similarly, if you were to take the example of the Facebook data, right? We talked about the Facebook signal. So here is, if you have if you are working at Facebook, okay, and by working at Facebook, I don't mean just checking your Facebook page. You are really trying to make money for Mark Zuckerberg. Right? So what kind of, the data is everything that you do on Facebook is a signal. What kind of information you can extract out of that? From Facebook's perspective, the question they are trying to ask is, what kind of ads should I display to you? Those ads that will interest you and you will click on them and they will get some money. So for Facebook data, signal processing can, the information that you want to extract is what ads to display to a user. And there are many other countless examples that you can think of. Okay, so having defined signals and signal processing, then the next question becomes how to extract information or manipulate signals. Now, it completely depends upon, it's a very, very subjective question. It depends upon the type of signal that you have and the desired information that you are after. And that is why you will hear in the signal processing world, people will actually become specialized in certain applications. So you will hear terms like, he is a speech signal processor. What does that mean? Well, they are expert at signals that corresponds to speech or music, and they have learned really in-depth details of how to manipulate those kinds of signals to achieve desired effects. Okay? So if you were working at, for example, Bose, everyone knows what about the Bose company, which makes these noise canceling, really expensive headphones, right? That as long as they are paying the engineers well, I guess then they are worth it. If you are working there, well, you better be an expert in terms of speech signals and how to do manipulations of that. Right? Or you will hear the terms, this guy does image processing. What does that mean? That means that that person really understands the signals that correspond to images and how to manipulate them. Okay? Or this guy does financial signal processing. So in the Wall Street, if you go, you can use signal processing background to try to make money for these hedge funds. And for that, you can't simply just take your tools of signal processing and go there. You also have to learn some application specific things. So people who do financial signal processing have become really good at understanding financial signals and what kind of things to do to extract information out of that. Okay, so the answer to this question of how to extract information, it is really application dependent. Okay, and what signal processing does is it provides you a collection of tools. So this is very much application dependent. And signal processing is going to provide you a large collection of tools. Each one will be suitable for certain tasks. And that is essentially what we will do. We'll keep on learning about new tools. Now, not all of those tools will be applicable to all applications. And how do you learn which tool to apply where? Through practice. Okay? You work hard enough and then you know. It's like when you are in elementary school and the teacher starts teaching you addition. And then you learn multiplication and division. And soon you grow up and you don't even think twice and you know what kind of setup requires addition and what kind of setup requires division and multiplication. It's the same sort of things. We'll learn a lot of tools in this class. Now, those tools will still be very small fraction of what signal processing is really about. Okay, I just want you to be aware of that thing. I also want you to be aware of the fact that it is you who has to decide how can I use this tool to X application or Y application. Okay, signal processing is an exciting field because it has connections with so many other areas. If you pick up any application today, pick up any device that you have. How many of you have got smartphones with you? A large fraction. Well, none of the smartphones that you have will be as good as you see them if it was not for signal processing. You may not realize it, but pretty much every aspect of smartphone relies on signal processing. Ranging from your voice that you speak and it gets encoded to transmission over that combination with it's called signal processing for communications. How you take pictures with your camera. Okay, Apple just acquired essentially a one-person company who was actually doing research in signal processing and made this app which takes really fast photos in iPhone. And it's all based upon signal processing ideas. If you go and read, he's talking about discrete cosine transform and JPEG imaging and all that. So pick up any other device. Your HD TVs, they rely on signal processing. Your Kinect, if you play Xbox, it's relying on signal processing. Security devices, MRI machines, ultrasound machines, all of them have become digital and all of them are relying on signal processing. Okay, so it's an exciting area and we are only going to touch upon very few aspects of that. And the message I want to take you to take from here is that signal processing is everywhere. If you feel excited about it, you just have to go and read more about it in terms of applications. We unfortunately can only touch upon a very small fraction of what it exists. Okay. So let's look at the simplest picture of signal processing, what it looks like in terms of a block diagram. The simplest picture looks like you have an input, and then that input goes through some block in which we do processing and we get output. Now, any block that takes as input a signal and generates an output, what is that called? Effectively, this block will be calling that system, and that's where the term system, which you probably studied in your last class, comes in. Formal definition of a system is that anything that takes some inputs and I'm putting S in brackets because it may take one input or it may take more than one input, okay, and generate some outputs is a system. So signal processing is really about designing systems. You are given a signal, you want to achieve some desired outcome, well, you need to make a system. And what does it mean by making a system? It does to the input signal what you want it to do. Okay. Now, a system in turn can be made up of many subsystems, and that's what signal processing system looks like. So we'll often be calling it something a DSP system, but itself it will be made up of many subsystems. So a DSP system is made up of many subsystems. And what we'll do is try in this class, try to understand the characteristics of some of those subsystems. In particular, we'll look at one key component of that subsystem, which itself we'll look at it in terms of designing a filter. Right? So one key component of a DSP system, in most DSP systems, will be a filter. And we'll understand what that is. Now, just to make sure we understand from last class, just like signals, systems can be natural or man-made. So one example of a natural system will be a brain. Anyone's brain, it takes as input, we have, you can, if you want to be conservative, you can say we have 5 senses that go as inputs, and as outputs, we generate some actions, right? So a brain is a natural system. It takes as input, it generates an output. You can't write a mathematical model for this brain easily, although many people, it's an ongoing research, but it is a system nonetheless, right? It's a very complicated system, but it is a system. So senses are its inputs, and this system takes more than one input. We know that. And actions are its outputs. So I hear a voice, that's an input, and I look around, that's my output. Right? A system that all of us use, which is man-made, is a cell phone. One example of input on that cell phone will be I'm talking, so my voice is the input, and then in turn that cell phone is transmitting some signals that are going to the base station that are then transferring over to the other party, right? So the radio transmissions are the output of that cell phone. Okay. So my voice in a cell phone is input, and the radio signal is the output. And if you are doing Skype, then actually you have now 2 inputs. You have your voice and you have your image. Now, we have talked about signal processing. Let's quickly try to think about what is, so the name of the course is digital signal processing. So let's ask ourselves, what is digital signal processing? And the answer is the block diagram stays the same. Okay? But the question of where that processing happens defines whether it's just signal processing, or you can call it analog signal processing or digital signal processing. So a signal processing system in which the processing happens inside a digital system, inside a microprocessor, that makes up a digital signal processing system. Okay. if you have a system which does processing, but it uses analog components. What do we mean by analog component? Resistors, capacitors, inductors, okay? Signal processing systems used to be built that way. So that will be analog signal processing. So signal processing in which, and I'll be using the abbreviation SP for signal processing often, in which all the processing takes place inside a digital system. And digital signal processing, then by its very nature, it will require a digital hardware and some software. And the flip side of that is that you will have analog signal processing. Now I want to make it clear that DSP system itself does not mean it has no analog components. DSP system will have analog components to interface to the analog world. So most of the time, the signals that you deal with are going to be analog. If I'm speaking, my voice is analog. So to take it into the digital realm, you have to have some analog components in your system. But the processing, where the processing happens determines whether it's digital signal processing or analog signal processing. So I want to be clear that DSP systems can have analog components. But their purpose is to interface the analog world to the digital world. Okay. And the analog components don't do processing. We'll leave at here because we have run out of time. But basically, what we want to talk about in the next class is, that's great that DSP system means processing inside a digital system, but why do we want to do that, or why is DSP better than analog signal processing? Okay, we'll take up from there in the next class.